Okay, Friday is the exam. Two, and the topics are everything up through pure tension and compression. After the test on Friday, the assignment for the weekend is going to be related to pressure vessels. That is also pure tension compression, but we haven't done those yet, so that's not going to be on there. So not pressure vessels. Tomorrow, sometime tomorrow, yeah. But yeah, Monday is fine. Anybody who wants to take it Monday, we can work that out. Yes, that would be the best. Yeah. Right. That's right. Any questions about the test? 3 or 4, yeah. Almost always 3 or 4, I'd say, on exams. Okay, anybody have any homework questions that are related to the test that you want me to do? Okay, do you have it with you? I didn't bring it either. Yeah. Thanks. Okay, that's a big one. All right, so yeah. So that's the one like this. And you have a roller over here and a member here. And there's a 400 Newton force applied that way and a 620 Newton force this way. And all of the angles are 20 degrees. All the acute angles anyways. So that means that the other ones are 140 if we need those. Okay, and the cross-sectional area, a couple of people have asked me about this. It's not given. Let's say if you haven't done it yet, if you have done it, then whatever you use is fine. But the cross-sectional area, let's say that it's 0.001 meters squared for every member. All right, so I'm going to first label these pins. So I'll call this A, B, C, D, and E. And when I went through the steps on how to do a truss, I said first isolate the whole thing and do that as a rigid body. You don't have to do that actually. I mean, it's as good a first step as any, but you could also just isolate individual pins. And I think you could do it without solving that as a rigid body, if you isolate that pin, isolate every pin, it'll give you enough equations to solve. But I guess I'll do the rigid body first. So first, a free body diagram of the whole thing. We have a force vector here. We don't know the direction, so I'll call that RA. We have the 400 Newton force, the 620 Newton force. And then at the roller, that force is perpendicular to the ground toward the body. So I'll call that N. And since we have only 3 unknowns and it's a rigid body problem, we'll have 3 equations. So we should be able to solve for all those variables. So I'm going to do it the way I do it in statics. I'm going to write out rho. Rho force moment for each one of those loads. Let's see, I'm going to put the about point here. So then for that force RA, the rho vector is 0. The force vector is RAX, RAY, then the moment is 0. That's the Z component of the moment vector. Next, I'll do the 400 Newton force. The rho vector, well, all we need for that is the height, the vertical distance between, because that force is horizontal. So that is going to, what are the lengths of these? It's more complicated than that, isn't it? 2.5. No. So 1.2, it's more complicated. So we got to figure out that height. It's going to be 1.25. So 1.25 over h is equal to the cosine of 20. So 0.940 is equal to 1.25 over h. So h is 1.25 over 0.94. Can someone tell me what that is? 329. Okay, so the rho vector, we don't care about the x component. The y component is 1.329. Call that 1.3. And then the force vector is 400, 0. And so you get negative, what do you get? Multiply 1.33 times 400. Okay, 5.32. 100. 532. And then the 620, that's at, okay, so the 620. The rho vector, we don't care about the vertical component. I guess we know what it is anyways. It's 1.33 up, and it's over 3.75. The force is 0, negative 620. So what's 3.75 times 620? 2325. And then the last one is that normal force. The rho vector is 5, 0. The force vector is 0, n. And so the moment is 5n. So Newton's second law says RAX, RAY plus 400, 0, plus 0, negative 620, plus 0n is equal to zeros. And then the moment equation says negative 532 plus 2325 plus 5n is equal to 0. So what do you get for n? Yes, thank you. So this should be, so these should both be negative. And if you're thinking about the answers you get at each step, we would have seen that when we calculated that n value and saw that, you can't have a normal force that's pulling. We would have gotten a negative value for that n, and that doesn't make any sense. So what, 2857 divided by 5? 571.4. And then that's Newton's. And then we can use that to calculate the reactions. So that RA vector is negative 400 for x, and 48.6 right, 48.6 positive, right? Okay, so now we can isolate the individual points. So let's say, let's do a free body diagram of A to start with. Well, we know that we have that force vector, negative 400, 48.6. And we know we have, I'm just putting it down here because otherwise it'll get cluttered. We know we have this force that I'll call F1. Why don't I name these? So I'm going to call this member 1, 2, 3, 4, 5, 6, 7. So we have F1 there, and we have, that was F2, right? And those are all the forces on that pin at A. So Newton's second law says we have F2, 0 plus 0.940 F1, 0.342 F1 plus negative 400, positive 48.6. That's equal to zeros. So from the second one, what do you get for F1? 48.6 divided by 0.342. So negative 142.1 newtons. The negative means it's compression. And then plug that into the first one, and what do you get for F2? Okay, 540.7 newtons. So we have those first members. And so what we got is that member one. We get compression for member one? That doesn't make sense. That doesn't seem very likely to me. Let's see. It sometimes can fool you, but with this big 400 Newton force here that's trying to stretch that, I wonder if I made a mistake somewhere. Well, I don't know. I'm not going to find it now, but this is the approach to take. You might not want to trust those numbers. Let's just go up to another one and see how it goes as you keep going along. So now we know member one, and we know member two. So you can see if you go up here to the pin at B, we know one, which means there's only going to be two unknown forces there, 3 and 4. And if you have two unknowns, you have two equations, so you can solve that, and you can just sort of hop around. The other way to go, so this is kind of the way that works well if you're doing it by hand. If you're taking advantage of the fact that you can solve this as a big system of equations really easily on your calculator, you don't have to isolate the thing as a rigid body to start with. You can just isolate A, then isolate B, then isolate C. You have a big system of equations that you can solve for however many variables. And it takes sort of it takes the creativity out of it, but it also takes the guesswork or whatever. It's basically like you could write a computer program that way that would work for every one of these, which maybe you should try to do. Yeah, so let me just show how to start. So another way to do that. Okay, so at that point you just continue on. But another way to solve would be, so let's just start by isolating the pin A. Okay, so what loads are acting in A? There's an unknown force vector applied by the pin, and then there's a tension from 1 and a tension from 2. So just right from the start, we can write this as, so there's an F1, there's an F2, and then we have this unknown force vector that I'll call RA. That's 4 variables, so we're obviously not going to be able to solve that. But Newton's second law says 0.940 F1, 0.342 F1 plus F20 plus RAX, RAY is equal to zeros. And so if we're going to set this up as a, in an augmented matrix and use reduced row echelon form, we can write this as our first two equations. So we have 0.940 F1 plus F2 plus RAX is equal to 0. And our second one says 0.342 F1 plus RAY is equal to 0. That's equation 1 and equation 2. And now we go on to the second one. So at that joint B, and notice that, so when you isolate the pins, you're treating those like particles. So there's no rotational Newton's second law, there's no moment equation. You only get 2 equations per pin. if you isolate the whole thing as a rigid body, then you also have to do the moment equation for it. But this way, we're gonna have our number of equations catch up with our number of variables using only Newton's second law. So pin B, what do we have? Force 1, force 3, force 4, and a 400. Okay, so we have the 400 Newton force. We have F1, 1, 2, we have F3, and F4. And Newton's second law says 400, 0, plus negative 0.940 F1, negative 0.342 F1, plus F4, 0, plus 0.940 F3, negative 0.342 F3, is equal to zeros. So you get two more equations, you know, equation 3, equation 4. I guess let me write these out because this is the first one that has a constant in it. So equation 3 would be negative 0.940 F1 plus F4 plus 0.940 F3 is equal to negative 400. Do the same idea for 4. Keep going, and eventually, let me do the last joint. So when we get to the final joint, E, we have let's see. So we have member 6 and member 7, and then the reaction from the roller. So we have this force F6, this force F7, and then the ground is horizontal, so the force at the roller is this. I'll call that RE. Or I guess, what did I call it before? Normal. I'll call it N. Do Newton's second law. Okay, so how many equations and how many variables do you have? Well, you know that at each joint you get 2 equations. So 2, 4, 6, 8, 10 equations. Okay, and now count up the variables. The reactions, you have 2 here, because that's an unknown force vector. You have 1 here, so that's 3, plus 7 members. You're getting the tension in each member. So 3 plus 7 is 10, and you can solve the system. So it's kind of up to you. I mean, you can, if you have a way that you liked from statics, do it that way. If you want to calculate, do the rigid body analysis of the whole thing and then go to joints and see what you need, do it that way. If you want to just go joint, joint, joint until you're done, do it that way. Whatever works. Yes, 10 by 10. And the augmented matrix would be 10 by 11, yeah. So, but 10 variables, 10 equations. And a lot of times you can sort of pick through there, even in a case like this, if you wanted to. It usually wouldn't take too long to do like sort of substitution, because you'll have a lot of equations that only have 1 variable, and then you'll have some that have 2, but you plug in the last one. But once you get used to doing reduced row echelon form on your calculator, it's so quick and easy, you might as well just come up with the big system.
There was something on an exam about go to the joint method, or not the joint method, the flipping method.
I don't care how you do it. Yeah, nobody in here took statics with me, right? Did you, Charles? Okay. Well, in our statics class, we tended to do things pretty differently, but it came up with a much bigger system. But yeah, as long as you can make it work, you can use any method that you want. Okay. Any other homework questions? So once you get this, then to get the stresses, you can think of all these members as oriented this way compared to the coordinate system. You know, like you don't have to think of them in the old coordinate system where some of these are at angles. That doesn't matter for this analysis. It'll come in, yeah. So, you know, if member 1, you have something like this, member 2, you have something like this or whatever. You just go through, and then for each of these, in this orientation, the XX normal stress is going to be, you know, F1 divided by the cross-sectional area. And so the stress tensor is going to be, since each of these only has normal stress along the x-axis, the stress tensor is going to be, you know, whatever this is, zeros everywhere else. And then you could use that to calculate the max shear stresses. Well, notice, I mean, I guess you've seen stuff similar to this before, but like in statics, you're used to being able to look at something like this and figure out what the maximum forces are. But if these have different cross sections, you could have different stresses in these. Like if you had a really thick steel member here, but you had a thin hollow tube here, you know, even though the force might be bigger on this one, the stress would be bigger on this one, you know. So we're just taking another step towards being able to say, like, where are we concerned about this thing breaking? Okay. All right, so last time we were talking about internal loads. So back to internal loads and beams. And this is not on the exam. And where we were was we came up with a beam where we had like a roller somewhere, we had some kind of force applied. And we wanted to analyze what the internal loads were at this point here. Okay. So let me go back to a similar example and let's just do that. So the question is, oh, and there was also a torque. Let's include that. So 500 Newton meters. We want to know what are the internal tension or compression. Oh, we were first going to just do it Okay, sorry. We were first just going to do it. What are the loads applied to the left piece left of that red line by the material on the right. That's what we're getting at. And remember, the way that we did that is we assumed that this is a fixed joint between those two pieces of material. And a fixed joint is capable of applying a force along every axis and a couple about every axis. Okay, so let's say we have, so I'll do that same thing. I'll just give some dimensions. So let's say we have a roller at the midpoint. The line where we want to calculate the internal loads is here. Let's say that's 0.25 meters. It's another 0.25 meters to the roller. And then it's half a meter to the end. And at the end, there's 1,000 Newton force acting down and a torque of 500 Newton meters twisting it. Anyone have a sense for like what a Newton meter is, like how strong a torque that is? Anyone have a ballpark figure for what kind of torque you could apply with like a screwdriver with all your might? Yeah, right. That's what I mean. Like, yeah, probably people have foot pounds and stuff. Yeah. Well, I'd say this is the thing that I think of to remind myself what that means. With a screwdriver, I can apply a torque as hard as I can with one hand of somewhere right around 10 Newton meters. Okay, but I'm probably stronger than you guys. Okay, so the first thing we have to do is calculate the external loads. So first I'm going to do a free body diagram of the whole beam. There is an unknown reaction force from the pin. I'll call that RA. At the roller, at the midpoint, there's an upward normal force. Call that N. And then we have these other two external forces, the 1,000 and then the 500 Newton meters. And now this is a rigid body problem to calculate those external loads. I'm going to put the about point here. And a lot of you guys have seen this in dynamics, or Charles has seen it in statics, but for rigid bodies, you can always write out this table with a row vector, a force vector, and a moment vector for every load. For me, it helps me just sort of keep track of what's going on. What we're going to see is that with this kind of problem with a horizontal beam, it's pretty easy to just do it in your head by thinking about, okay, that force causes either a clockwise or a counterclockwise rotation around that point. But I'm going to start out by doing it in this sort of formal, full way. So first, that force RA. RA acts at the about point, so the row vector is 0. The force vector is RAX ray 0, and the cross product is the 0 vector. Then that force n, the vector from the about point to where n is applied is positive 0.5, 0, 0. I'm using x horizontal, y vertical, and that means z is coming out towards us. So the force vector is 0, n, 0. And the cross product is 0, 0, positive 0.5n. And then these other two, I guess I'll do the 1,000 Newton force first. The row vector for that is 1, 0, 0. The force vector is 0, negative 1,000, 0. Cross product of those two vectors is 0, 0, negative 1,000. And then the last thing is that couple. For couples, the about point doesn't matter. The net force is 0, so these go away. Yeah. Did I say 1,000? Negative 1,000. Oh, sorry. And okay, so what's the direction of that couple? Well, if you have it drawn like this, that just says that it's in the positive x direction. So this is going to be 500, 0, 0. And now Newton's second law, you can just add up all the forces in the force column. We don't have any in the z direction. See, that's 0, that's 0, that's 0. So the only places where anything's going to happen are the x and y axes. So we have rax, ray plus 0n plus 0, negative 1,000 is equal to zeros. Ooh, we're missing something important. If this was all the loads that were happening, there's no way this could be an equilibrium, because if you're applying a torque of 500 Newton meters and there's nothing to resist that motion, it's just going to spin. So we also have to consider a reaction torque. I'll call it fancy TR. It will end up being the other way, but I'm just going to put it in the positive x direction and let the signs work out on its own. Okay, so this is TR. Again, this is a couple, so we don't care about that stuff. And we just have TR 0, 0. What's applying that couple? Well, the idea is if you have a hinge here, imagine like a physical pin going through that member, that would keep the member from turning this way. Okay. Okay, so that didn't affect Newton's second law, but it will affect the moment equation. So rotational Newton's second law, I'm going to do it in the x direction and the y direction. So the x direction says 500 plus TR is equal to 0. So in other words, TR is equal to negative 500 Newton meters. And then the moment equation in the z direction says 0.5n minus 1,000 is equal to 0. And so n has to be equal to positive 2,000. And now we can plug that into Newton's second law, and we get that this vector RA has 0 for an x component and negative 1,000 for a y component. Okay. So that's sort of a interesting thing. In order to have rotational equilibrium met, even though, like in a sense, these are resisting a downward force, you might think that they'd both be applying upward forces. That's actually going to, the way it's going to have to work is that that pin is going to have to pull down on this member to keep it from rotating. Okay, so now we have the external loads. Now we're going to calculate the internal loads. So free body diagram of the left, like everything left of the red line. So that's the piece. And then there's all this stuff that's not included in our free body. And that includes the downward force, that couple. But what is included is a downward force of 1,000. That's the RA that we calculated. I'm just gonna write that as a downward force of 1,000. And a couple this way of 500 Newton meters. And then the internal loads, which you can think of as, since the connection between what we're including and the light blue part that we're excluding, we can think of as a fixed joint. You can treat this as a force vector. For now, I'm going to call that R. So that's an X and a Y component. And then a couple, I'll call that M. And then a torque about the x-axis that I'll call fancy T. Yeah, it's just the different axes. So this is about the z-axis, and this is about the x-axis. I could have just written that as an M vector that just has couples for every component. We're never going to deal with couples in these problems about the y-axis. So I'm just going to call them separate things for x and y, or x and z, sorry. Sure. Yep. Okay, so now let's go to Newton's second law. You could write out the row vector, the force vector, and the moment. I'm going to make this the about point, and that's where I'm always going to do the about point and these kind of things. So Newton's second law says we have a downward force of 1,000. So 0, negative 1,000. And then we have Rx and Ry. Nothing else is a force. The other stuff was couples. So this is equal to 0. And so that internal load R is equal to 0, positive 1,000. And then we'll add up all the moments in the z direction. I don't know why I'm doing z first, but it doesn't matter. They're separate, they're uncoupled. So in the z direction, does that 1,000 Newton force apply any moment? Nope, not with that about point. It goes right through the about point. Does the x component of r? Well, there is none. It wouldn't anyways, because its line of action goes right through that about point. The y component does. Okay, so we have a force of 1,000 newtons times a moment arm of 0.25. And would that upward 1,000 Newton force make it rotate clockwise or counterclockwise around the about point? Counterclockwise, so that's going to be a positive moment of, 0.25 times 1,000. And then the only other thing that produces a moment about the z-axis is m. So we have plus m. And that adds up to 0. So that internal bending moment is equal to negative 250. Any questions about that? Yeah. And then the last thing is the x component of the moment equation. The only things producing moments about the x-axis are couples. So we have the negative 500 and the positive t. They add up to 0. And so that internal torque is positive 500 Newton meters. Okay, so that's the idea, except we did all this work and just calculated the internal loads at this point, okay? And normally you want to know, you'd want to look at this and calculate where it's most likely to break. What we did could help us calculate whether it's likely to break at that point, but we don't know how it's going to change as you go across. So the first thing that we'd like to be able to do is calculate those internal loads as a function of x as you move along the beam, okay? The second problem is notice that the way we calculated those internal loads, like we just used vector components for the couples and the forces. And we got these internal loads like we wanted. But think about what would happen if we arbitrarily chose to isolate the left part and calculate the loads applied to the left by the right. We could have just as easily isolated the right and calculated the loads applied by the left. Would we have gotten the same things if we'd done that? How would it change? Just different signs. Yep, because of Newton's third law. Okay, and so we're going to do the two next steps are so the first one is we're going to introduce a new sign convention. For these internal loads. And what this sign convention is going to do is it's going to make it so that no matter which part of the beam we isolate, we get the same answers for what's happening at a certain point. That's preferable, you know. So that's to deal with getting different answers in the different directions. And then the second thing we want to do is the function thing. We want to calculate these internal loads as mathematical functions of x. So that then we can like look at this function or graph it out or whatever and say, okay, this point right here is where we want to check and see if it's going to break. If it's good there, then we're good over the whole thing, you know. So we have the test on Friday, and then on Monday we'll do this.